Let us begin our study of algorithms with the first kind of algorithms known as brute force algorithms. These are, in a sense, the simplest possible algorithms. The idea of a brute force algorithm is to simply don't do anything smart. In a sense, these algorithms simply do the most obvious thing in computing a solution to the problem. Brute refers to an animal. So these algorithms behave like animal forces, simply going through the motions without doing anything smart or intelligent. So in our to use our terms, they don't use any smartness or what we call yukti, right? Instead, they only use force or what we call shakti. So these algorithms are simply the simplest and the most straightforward solutions to the problems. So what they do is they exhaustively check all options. For example, if you are searching for a house in let's say a city like Bangalore and you don't know the address of the person, if you go to every house in Bangalore one after another and compare the person in that house to the person you are searching for. The person you are searching for, we call it the key. The person who is there in that house is an element of data. So you compare the key to every element of data. You go from house to house to house looking for that person. That would be a brute force search algorithm for finding a house in Bangalore. That is normally how we don't do things. There must be smarter ways, but first let us study these brute force algorithms. So as I said, these are straightforward approaches to solving a problem, and you can say that the idea or the philosophy of brute force algorithms is just do it. Don't try to be smart. Don't apply any intelligence. So as a rule, these are not the most efficient algorithms. In fact, these are the most inefficient algorithms for solving most problems. Let us look at a particular problem called sequential search. So here, like I said, you are searching for a key in a set of data elements. So you are given a key k, let's call the key k, and then you are given an array of n elements. And the objective is to find the index of the element. Which element in the array is equal to the key k. So we need to compare k to each element of the array. There are two possible outcomes. We either find the element, in which case it's a successful search, and we usually return the index of the element in the array, or we reach the end of the array, in which case we conclude that the search was unsuccessful. That is, the key was not present in the given data elements. Suppose you went to every house in Bangalore and you still did not find that person, then that would be an unsuccessful search, right? Can we do anything better than this? We make a small improvement, right? Why do I need to consider these two cases? Is there a way to combine these two cases? How do I combine these two? Suppose I guarantee that you will always find the element, right? To do this, we make a small modification to our idea of this sequential search algorithm. We simply add the given key, k, as the last element of the array. So we make it the n plus 1th element of the array. Now if you are going through the array elements from 0 to n sequentially, you are guaranteed to find this element at the end. So now if you found it before the end of the array, then it's a successful search. But if you find it as the n plus 1th element of the array, then it's really not a successful search. So success now is, you will always find the element, but success is now determined by whether you found it before the n elements or as the n plus 1th element of the array. Let us try to write an algorithm for this, right? So sequential search takes an array of elements 0 to n and the key k which we are trying to find, right? So what we do is, with the modification I suggested, we first write the key k as the nth element, as the n plus 1th element of the array. So you notice that this array has now n plus 1 elements, 0 to n instead of 0 to n minus 1. So we assign k to the n plus 1th element of the array, and we start at the beginning. I equals 0 means we start at the beginning. And all we do is, while ai is not equal to k, that is, while the current element of the array is not equal to the key we are looking for, or in other words, while the person you are looking for is not present in the current house, go to the next house. How do we go to the next house? We do I equals I plus 1, right? Keep doing this. When do we exit from this while loop? We exit when ai becomes equal to k. Now that is guaranteed because we have done this part. We have assigned the key as the n plus 1th element of the array. So at some point we will find the key. So the exit condition for the while loop is ai equals k. So when that happens, you have come out of the loop. Now you check the value of I. If it is less than n, that means you have found one of the elements of the given array which was equal to k. So that is, the search is successful. You simply return the index of that element I. If I is not less than n, that means I equals n plus 1, that means none of the given elements was equal to the key k. The element which was equal was the one that you assigned here. So we return failure or minus 1 in this case. So for example, if the array had 4, 5, 26, 3 and 8 and the key k is, let's say, 3, right? Then what we do is we add the here, so here n equals 5. So I add the 6th element of the array as 3, right? And now I start here with I equals 0. That element is not equal to the key 3, so we move here. This element is also not equal. This element is also not equal. When we come here for I equals 0, 1, 2, 3, we find that the element is equal to k, so it would return the I equals 3 as the answer, as the return value for sequential search. On the other hand, if you are looking for some other element which was not present, then you would find it only as the last element which was artificially inserted by you, and then the algorithm would return minus 1. So this is how sequential search works. So how do we analyze the complexity of sequential search? How many times do we compare, right? In the worst case, we compare n plus 1 times, right? N times for the n elements of the array and 1 time for the extra element that we added. So this is the unsuccessful search. If search is unsuccessful, then we end up making n plus 1 comparisons. So that is the worst case. If the if you find an element before that, right, then the number of comparisons made may range anywhere from 0 to, right? So if we are making n comparisons, that would be somewhere between 1 and n for a successful search. If the very first element happened to be equal to the key, you would make only one comparison. If the second element happened to be equal, you would make 2 comparisons. If the last element happened to be equal to the k, then you would make k comparisons, right? N comparisons. So this number in either case is of order n. So it is a linear algorithm. Order n, we say, is linear. So the sequential search algorithm takes time or number of steps that is linear in the number of data elements given. Now, is that a good thing or a bad thing, right? For search of this kind, ON is bad. This is not a good thing, right? Imagine you have gone to, on an election day, you have gone to the voting booth to cast your vote, and then all they have in their computer system at the voting center, the polling booth, is an array of all the citizens of India, right? Or everybody who has a voting card. And then if they start doing a sequential search to find you in that list, there are 1 billion people and it would take forever, right? That is not a good enough solution. So later in other chapters, we will study smarter algorithms, not brute force algorithms, algorithms that do better than linear time, that are faster than order n. So if we want to do better than linear time, we need to have the array already sorted. So let's look at a quiz question where we look at searching for an array element where the array is already sorted, right? And what we do is we stop the search when the array element is greater than the key k. So if the array is sorted in ascending order and I am looking for a particular key k, then I need not go till the end of the array. I will stop when the current element is greater than the key k, because there is no chance of finding it in the remaining elements of the array. If the current element is already greater than the key, I have gone past the chances of finding the key, so I might as well stop. So in such a situation, which of the following statements is false, right? So option A is the worst case complexity is still O of n. Option B is the best case complexity as O of 1. Option C and D talk about the average case complexity. Average case here means I look at a large number of instances of this problem. That is, take lots of different arrays and I'm looking for some random element in those arrays which may or may not be present. So we select different arrays, different keys, a large number of instances, and on an average, what will be the complexity or the number of steps involved in finding the key k in the array, given that the array is already sorted. Option C says the average case complexity is O log of n, and option D says average case complexity is O of n. Now, out of these four statements, 3 are true, 1 is false. Which one is false? The option A is true, because in the worst case, either you are looking for the largest element in the given array, or you are looking for an element which does not exist in the array. In both of those cases, you will go till the end of the array, so it is still order n. Best case complexity is O of 1. This is also true, because in the best case, you are looking for the smallest element of the array, which happens to be the first element, so you can find it in one step, right? What about the average case? There is no way that the average case can come down to log n. It will still be order n, because what happens is if you take a large number of instances, on an average, let's say you will find the key midway in the array. So it will be n by 2 comparisons, which is still order n. N by 2 for a large n is much greater than log n. Right? So statement C is false, A, B and D are all true. Thank you.